Hi everyone, welcome to this workshop. I'm Pedro. I'm an assistant professor at Tecnico, Lisboa in Portugal. My background is in chemical engineering, which differs a bit from my colleagues. And I started being interested with open data by the means of open science. So I started to really get interested in the science and the need we have to open it, and only then I digged into the data aspect of it. Today I will try to give you we'll aim at hands-on workshop. There'll be a first introductory part. Then we'll have a first drill or exercise, which is more a brainstorming. And in this, after another quick, let's say, introduction to data sharing, we'll have a second exercise in which we'll really get your data set to be shareable with the community. So thank you again for joining. Today's about data sharing and data management, and I will start a bit earlier than that, because as I told you also, my motivation for sharing data comes from open science, and I guess from most people that can also be the case. And obviously we need a good motivation to share data in a good manner. So I'll start indeed from the perspective of open science. I don't know if you are aware. I'll try to get rid of this. Okay, perfect. So I don't know if you are aware, but there's a lot of data sharing behind the story of the periodic table. For instance, Sir Humphrey Davy was a founder of 5 of the elements in the periodic table, like sodium, potassium, and he did it about 60 years earlier than Mendes put up the table together. So what did he do? Sir Humphrey Davy had no clue that the periodic table was coming later, and he put all his findings with experimental procedures, the observed data, into a book called Elements of Chemical Philosophy. And it was this book that 60 years later, Mendes took, one of the books, of course, took to put the periodic table together. So to get to this periodic table, or the periodic table as we know it today, we needed indeed quite some data curation. Some elements were even discovered in the centuries before, and we need this data to be shared, curated over to Mendes. But that's quite a powerful story in chemistry and material science on what data sharing and data curation can do. Now, today, there's a crisis on science. Some people would argue. I would concur with that. There's the publish or perish pressure for publication. So that's there with the great evidence. There's the typical stories about co-author ships coming out of that, among other examples. And there's also all the stories about reproducibility that have come to publications, even in The Economist, also in many scientific journals. We have been talking about the reproducibility, the problem we have to reproduce other scientists' results or other studies. If you go to today, data sharing. So I told you about the periodic table. Let's see what are we doing today in terms of data sharing. There are quite some differences across fields. So I went to Dimension, which is the database of publications, but also data sets. And here you can see that the average in yellow. So this is a data set to article ratio, which gives you the feeling how many data sets are published per article. This is multiplied by 1,000. So you see, on average, in the last couple of years, there's 40 data sets published per 1,000 articles. So that's 4%, which is quite low. There are some fields doing better. That's, for instance, in biology, you can see that's about 10%. So it's already a more reasonable number. But you also see that other fields are doing much worse. And here we are in engineering as average, and materials engineering is not any different from the average engineering field. So we are sharing only about 7 to 8 data sets per 1,000 articles. That's very few. We are basically not sharing the most part of our data. So that will not provide all the answers to the reproducibility crisis, but of course, having the data will for sure help reproducing it in a better way. Now, we need to change the status. We need to share more data, and we need to make science work in a slower, or at least in a different and most likely in a slower manner, such that we don't face that we overcome the reproducibility crisis. There's quite some institutions working on this. There's DORA, which is the Declaration on Research Assessment, which tries to change the way publications are assessed. There's some groups of universities, LURU, which is pushing for different ways of evaluating science. And for instance, the Royal Society of Chemistry implemented more diverse awards, which will also promote other types of scientific outcome other than papers, and also foster data sharing. Also, governments and funders are pushing for it. They are pushing more and more for open science, and so for papers to be open access, but also for data to be shared. So I guess, yeah, I do believe there's a revolution on the way when it comes to open science and open data. So what is open science really about? First, it's about breaking any barriers to knowledge. So anyone can access the knowledge regardless of the kind of software, paywalls, removing all paywalls that might exist, and so on. And it should also turn out to improve the collaboration in science. If everything is open and I can check the work of someone working in the same field somewhere else in the world, it will be easier to collaborate. If things are behind paywalls, we are making it much more difficult. For COVID, it was a huge case study for this. I think it's quite obvious today. For instance, in Zenodo, which is a European repository, open repository, there was a community created in which a lot of data sets and papers were shared, but there's tons of other examples about how sharing was spurred or was improved by COVID pandemics. So you know now what is open science is about breaking barriers to knowledge. Why should we do it? We talked about the aspects of quality and integrity in science. There's also aspects, of course, of economic benefits. If knowledge is open, there can also be benefits from this open knowledge. Also, to decrease asymmetries over worldwide between countries, as there will be no paywalls. Of course, most people also believe that this will also improve citizen science, so citizens can have access to the information and make also use of it to better improve their own lives. There's of course innovation that will come from this, and efficiency. Yeah, if the data is open, I will not, especially we are talking about efficiency a lot for negative results that today are not published in journals and will always be published in a data set. And that will make that I don't have to repeat results that were negative, and today I'm not aware because they were not published. So there are various reasons to go for open science, and there's various ways of doing so. Or more concretely, there's you can do it for many of the outcomes in science, or in other types of, or also in private research. So you can, starting from the right, even when you do a literature search, if you compile some articles on a given topic in an original way, that can be worth sharing with the community in an open way. When you analyze data, that can also be worth sharing as it is, applying machine learning methodology, let's say, to your own data set. Then if you write it, of course, there's what we already know today, preprints became quite popular nowadays. Then in the publication stage, there's the classical open access, but you can also share most of the times the papers within some embargo period with the community. Then there's outreach. So this presentation will become open and you will be able to see it. This scheme that I'm just presenting is also shared openly with the license. So you can, everything that is outreach, everything that you are creating to the community can be disseminated openly and can be of use to anyone else in the world. So here there's a list that you can go through later if you feel like, I mean, I don't know exactly what to do. There's some tips, and there's also the link indeed to this content. And there's also an overview of the platforms in which you can do it. Of course, for data, we'll go a bit more into detail. So we started with open science. From that, we got to data being one of the types of scientific outcomes that we can share. And before going really to the sharing part, I would like to come from a bit the level above, which is management. Sharing is, of course, just a small part of management. So let us start by management, and then we'll move to the sharing just in some minutes. So data management can be seen as the management of the data life cycle. What are we talking about when we talk about the life cycle of data? So usually we have raw data. We can perform some information extraction to get what are the main trends, for instance, in that data. This can obviously be machine learning, can also be a more manual method, so to say. After we have extracted this information, we still want to take out some knowledge and share it with our community, with our company, write a nice report, understand what's wrong with this type of material, and so on. So we go through the knowledge divulgation stage, and at that point, usually what happens is we put the data to the trash bin. So either in papers as supporting info, because these are very difficult to use, or even in companies, this becomes part of a folder that nobody will remember about in the next few years or decades. So that's the end of the life cycle of data in most cases today. What of course we aim at with a good data management is that this data can be reused in an infinite cycle. There's no reason to not reuse data that was generated today or that is being generated today in 100 or 200 years. There's no good reason to not do that. So the goal is to close the cycle by reusing data via a proper data management. So what is data management about? Data management is in fact about actively taking care of your data throughout all the life cycle of the data set. This can go through various stages. Of course, the first step is planning. We need to plan ahead before generating the data, what we'll do with it, how we'll collect it, and so on. And of course, we go to the lab, we do our simulations, and we do collect or create the data. We need to process and analyze that data. We need also a way of storing that data, share it, so giving access either within our own institutions or to the open society or community, and then make sure that people do discover and reuse this data. So these tasks are all needed to have a good data management, but most important, we need planning. Right? At this point, you'll be having quite some data, most likely that you never planned for from the management perspective, and it will get more and more difficult as you go through this cycle, as you come to the end of the cycle, to perform an action on that data. Let's say that you have analyzed this, when you have analyzed the data and you didn't thought about what to preserve the raw data, it's too late to share the data in a raw format, for instance. So the key message is plan, plan, and plan. So that's what we'll talk in the next slide before moving to the first exercise. So that's the reason why also funders, governments, and institutional bodies do care so much about DMP, so data management plans, because planning is really the crucial step towards a proper data management. So I don't want to go too much into DMPs, because at the end they are a very important tool, but there is just that, a tool. But I want to give you a flavor of what are the things that should come up or you should think about when creating data or having insight to create data. You don't have to formally do a DMP for that, but you do need to think about all these topics. So first, think about the types of data you'll be working with, and which metadata, which is what context you need for people that did not create this data to understand it and to be able to reproduce it. We'll go into more detail about this later. But then you also need to think about storage, backup, and security. So storage and backup are quite important. Still today, people have trouble sometimes recovering old data or recovering their own data if they only store it once. There's the rule of three, in which you should store it in 3 different places, 3 different types of storages, and including one offline. But the point is that you should really think about storing it in different ways, such that there's no data loss. There you should also think about long-term access. If you are in a short-term contract, most likely it's data is in your personal folder. This will stop sometime soon. If you store it even in an institutional website from your company or university, will this always be there? That's a question you should ask yourself, and then make sure that you do find the right repository such that data is there for as long as possible. So we'll also go a bit more into that later, but make sure you do archive it in a repository that allows for long-term access. Then long-term access, I would put it more together with storage, but we need to give access to people we want to share the data with. So that can be, again, the open community, can be your colleagues in the same department, but we need to also design that access and then share it actively. Then there's just giving access and do the first sharing is not enough. We need to design also policies for use of this data. Am I making this easy enough? Am I really giving people the opportunity to reuse my data? Is it in such a way that people can easily reuse it? So these are the main topics to think over when you start planning about your data. There are quite some good tools online to create data management plans. So there are these tools that I suggest that you can just use, but there are also some info and checklists from universities. Also, Connie was mentioning about it at 4TU. So there's quite some information online. What I want to point out is you can also create your data management plan online under some conditions. So we started with open science. Here we came to the conclusion that clearly data is an important part of it, and we also need to make our data open to improve collaboration, to make science more reproducible. So now let's come to the practice of data sharing. Most of the things we'll discuss after, most of the discussions that have been around on how to share data come from the FAIR principles. The FAIR principles were set up in the Nature paper in 2016 by a huge group of scientists, mainly from the biology field, and they made the FAIR principles as guidelines to any community to make their own specific standard for data sharing. So the FAIR principles is always our let's say lighthouse. So FAIR stands for findable, accessible, interoperable, and reusable. And we'll go a bit more into depth now on these ones. So findable, it's on in a sentence data that can be found easily on the web, because that's where we'll find most of our data. But if you are in a private company, again, in the company database and so on. So data must be findable. Also, it should be accessible in the sense I know if I can access or I have the right or not to access this data. And I also know which use I can give to this data. So there should be a license given to the data. Interoperable means that it's easy to use from different software, but also that machines can for sure read the data. So that's a lot related with the reusability as well. That comes as a fourth pillar, because data also needs to be well described. So we also need metadata to make sure that when you reuse data, we do it in a proper manner. So interoperability is more about using the core data. Reusability is more about the description of that data via metadata. Here you can see a bit more. The quality is not great, but I will. I think I hope it's still okay. Here you can have a bit more of a longer definition about each one of these concepts for FAIR. And in the next exercise, you will be working with these concepts. So what you can immediately do is just take a print screen of this slide. Go ahead, and you will use this in the next in the first drill. It's about FAIR, and it's about learning from your own experiences. So the exercise, I will also share the slide later. This exercise is about learning how to share data from the experience you have in your own field. So what we'll be doing is, in the first instance, divide ourselves into breakout rooms. Then you'll be brainstorming individually, thinking about what is good in the way people share their data in my field, what is bad about that, and then we will have group discussions in the breakout rooms to come up with guidelines from that practice. What does that mean? Okay, yeah, if everyone in my field does share the data on a public repository, that's definitely a good practice. What is the guideline for other fields? What other fields can do? Let's say to create a repository that is field specific and that becomes well known from the community. So this is the kind of discussion we would like you to have, to be able to, from your own experience, draw guidelines to larger communities. I'll get to the next part and last before the second exercise. So we learned how to better share data. Now we will apply it to your own data sets. Before that, I will give you a bit more context on how to share data in a fair manner. So we have been we went through the FAIR principles just earlier, but there's more to be also said about that. I hope that the earlier discussion was useful for you to get a bit more into these FAIR principles, but there's already some standards for certain communities. Biology has these standards. Also in some material science subfields, there's also some standards. So if you want to know if there's any standard for your community, go to fairsharing.org, and there you can find community accepted standards. If there's not a community accepted standard, there's sometimes also just empirical best practices. So try to apply those when you share your data. So let's get a bit more into the practicalities. So about making your data set findable. Yes, so there you must describe the context, give context to your files via metadata. So it can be immediately just by describing what is the data about, which kind of materials were studied, as in the example here. Also listing all those materials and any acronyms, as you see here. So if you use acronyms in the file, either please state it in the metadata, or don't use at all. That is even better. Then interoperability, I think we discussed a lot about it. So it should be machine readable, should not be behind any paywall, and the format should match the data. That's something that also came out in the breakout rooms. Then the format is not so simple to decide. I mean, for tabular data, everyone can agree most likely on CSV, but still, for other types of data, you can go to the open air. So this is a website created by the European Commission, which has also information on other types of format that that might not be so obvious to you. And then there's also the 5-star data by Tim Berners-Lee, which put, for instance, CSV as 3 stars. To go above that on accessibility and interoperability, you should go to more generic type of formats as RDFs. So if you are curious about that, go also to 5stardata.info. Usability, we should always have in mind for usability that should be beyond the original purpose. So it's not only people that do the same kind of studies you do, that use it in the same manner, people should use it in other manners. From any other perspective, think again in 100, 200 years. So we should always share raw data, even if you did whatever kind of processing or analysis to your original data, you should always share the raw data with it. Also state any hypothesis and calculation details, most likely as metadata, such that people can reproduce this. And of course, any experimental procedures and operating conditions should also be shared as metadata. This is also valid for computer generated data like molecular modeling simulations. This should always be shared, preferably as metadata that is also machine readable. Then where should we share this data? I mean, there are also the suggestions Connie already gave. There's R3 data, which will give you, which is a repository of repositories. So there you can find repositories for your own community and all kinds of data repositories that exist. There's a generic repository that I keep suggesting just because it's public, funded by the European Commission, and very long-term access is granted, is also at the CERN labs. So this will be there as long as we can foresee. So if you have no specific option or no specific repository for your field, just go for Zenodo if you don't have a better choice to make. Just for me, this is my default option. Let's put it like that. Then there's also field-specific repositories here. For instance, in Zenodo, there's a material informatics community. It's not very active, but it's there. And anyone can create communities in most of the repositories. So check if there's communities that already relate to your field. There are also institutions creating databases. This is the high throughput experimentation for solar materials that is there, and you can also share your data. This was a suggestion that I took from Thomas' earlier presentation. But there are tons of field-specific communities and repositories. Make sure anyway that is open, that is really open. There are no barriers, that is findable. So people from your community should know this repository, or you should recognize it. And then that it really grants long-term storage and accessibility. So that was my main argument for choosing Zenodo. And then accessibility is about who can access and do what people can do with your data. And for that, you should always choose a license. And of course, you can go to Creative Commons to have some guidelines on that. But most open license is this one. So people can do anything with your content as long as they recognize and credit you for generating the original content. Then sharing or putting the data on a repository, it's not enough. As I was saying earlier, you need policies for reuse. We need to foster people to reuse it. So share the shared data, is the motto. So you can cite your data via the DOI that will be generated, but you should also cross-reference. You can cross-reference in the data availability statement in the paper. So this is now quite common and sometimes even mandatory that you have a data availability statement, and there you can put the raw data that corresponds to the figures or tables. And you can also, in the own data repository, link it back to the paper. That can be quite useful for people that want to know more about your data, but don't know that you publish a paper on it. So we went through the FAIR principles. I hope I made it a bit more concrete on how can you reuse your data, or you can make your data reusable, accessible, interoperable, and findable, where you also know now what are the different options. And don't forget that after sharing the first time, you should keep sharing and give ways of your community to find the data set. So now that you have all these backgrounds, let's get your data ready to be shared. So here we enter in the second exercise. Now we'll have people working in pairs. So breakout rooms will only have 2 people. That was already the case for some people. But so here the idea is that you work on your own data set with a checklist I will just send you in a minute. With that checklist, you go through the checklist and try to see if your data set is respecting those criteria, and if not, just make it towards those. Just make it work towards those criteria. Again, the moderators will be jumping from breakout rooms to help you making it a bit more concrete and give you some tips on how to get your data set even fairer. At some point, I will message you that, and you'll do a peer evaluation. So you'll take the checklist and check the data set of your peer in the same breakout room. Okay, so let's take, we are at, we'll be taking 20 minutes now for you working on your own data set, and then you'll do the peer evaluation and we'll wrap up at the end. Okay, so Ale will create if you could create a breakout rooms, that would be great. You live. And Ale still has something else for you. So let me just share my take-home messages with you. So I think it became quite clear that we need to fix science for reproducibility. Also, the way companies work needs to be fixed. I mean, there's plenty of experience for data that has been buried in files that nobody can find. So there's a lot for opening up science, but also for better managing data in companies. So that's all about good practice, but a lot about good planning. Planning is very important in data management. Beyond data management and the specific point of sharing data, there, especially for people that are in the research field, share as much as you are comfortable, but start sharing. So your files, I mean, the more fair, the better, the fairer, the better. But if they are still not perfect, but this is the time you have available, just share it. It's better than not sharing at all. So if you already even publish your data, still share the data sets, use open data instead of supporting information. Also share your code, your source code, so that people can reproduce your simulations, and also make preprints of new papers. Thank you. Ale will just send you a survey, I believe, to get your feedback on this session. I think it was hard work for 2 hours. We tried to get you from basics to really applying it. Of course, you will not be finished today, but with this presentation that we'll also share later, and with what we discussed today, I hope you are in a better position to just kick off your data sharing. Thank you all, and I'll be staying after the survey for people that will have a couple more questions. Thank you.
So I just feel like I want to thank you, everybody. It's amazing what you've done here. I think this is a big step for us and for research in general. And thank you, Pedro, and thanks to all the tutors, Yasmin, Paula, and Connie. And you can find the form. We created a very short survey. You can do it in 2-3 minutes, but that will really help us to get more information and get your feedback, and to be able just to make us able to make it better next time. So thank you again. And if you feel like you need some more support, I think you can stay for a few more minutes, and Pedro will guide us through some more instructions.